So hello dear student, welcome to the new video of this course, and in this particular video we are going to deal with the very last numerical on the clipper circuit. So we'll first see what kind of circuit it is. So as you can see, to the input side of the circuit we are giving phi sin omega t. That means we are providing a sine pulse having an amplitude of 5 volts, okay, and to that a resistor of 1k is connected in series, and after that as you can see, this is diode D1 which is connected in series with 3 volts, okay, and here as you can see D2 it is connected in it is connected in series with minus 2 volts, and D1 and D2 are exactly opposite to each other, okay. So this is what we can see. So let me copy the circuit and we will try to analyze this particular circuit, okay. So the very first thing whenever you encounter such circuit, okay, as I told you in the previous sessions as well, that whenever you encounter with such circuits, the very first thing that you should do is you should analyze this particular part, okay, this particular part and this particular part. That means whenever you encounter that the diode, it is connected in series with the DC voltage supply, so you should always analyze this particular part, okay. And the same thing I had done over here. Since our diode is silicon diode, so obviously the depletion layer voltage, that means VD, would be plus minus 0.7 volts, okay, and here it would be minus plus because here the N type is connected above and P type is connected below. Minus plus 0.7 volts, correct. So rather than writing 0.7 volts in this way, what I can do is I can write 0.7 volts in this way, plus minus 0.7 volts, and I will assume that this particular voltage, it is connected in series with 0.7 volts, okay, and that's why they get added. This is plus minus 3 volts and this is plus minus 0.7 volts. So you can assume that this particular 0.7 volts, it is extracted from D1. Similarly over here, rather than writing minus 0.7 volt in this way, I would write minus 0.7 in this way and minus 2 volts in this way. So this is minus plus 0.7 volts, okay, and this is minus plus 2 volts, and then it is grounded, okay. So as you can see, they both are in series and that's why they get added and we end up getting the voltage as 3.7 volts. Similarly over here, as you can see, they both are in series and their polarity is also same, so that's why they end up having we end up getting the voltage as minus 2.7 volts. And this is very important, obviously, as I told you in the previous lecture as well, that we have to see the voltage with respect to ground. We have to see the above voltage with respect to ground. Here also we are seeing with respect to ground. In the question I had intentionally not given minus 2 volt, okay, I had intentionally not given, but now as of now, like we know that whenever you encounter with the polarities, so you have to see it with respect to ground. So we end up getting this particular thing in this way, and then this is what we are going to analyze. See, we had done nothing. This was our circuit. We just added 0.7 volts in it, and then we changed this particular DC supply, that is from 3 volts to 3.7 volts, and similarly over here it was minus 2 volts, and by adding minus 0.7 volts, that is VD, that means the depletion layer voltage of diode, we end up having minus 2.7 volts. So this is minus 2.7 volts and this is plus 3.7 volts, okay. And after that, as I told you in the previous sessions as well, that whenever you end up getting this particular voltages, what you should do is you should draw the AC waveform. So you should always draw one AC waveform. So this is plus 5 sin omega t and then it is minus 5 sin omega t, correct. And as you can see, there are two voltages, plus 3.7 volt and minus 3.7 volt. So what you should do, you should mark those point over here. Let's suppose somewhere over here you will get plus 3.7 volts and somewhere over here you will get minus 2.7 volts, correct. And this sine wave has an amplitude of 5 volts, so this is plus 5 volts and this is minus 5 volts, correct. So I hope you understood everything up till here. Now another thing what I would like to tell you is, see, I will erase this particular thing because anyhow I had drawn this particular graph over here, I mean the input sine wave. So I will erase this particular thing, and then I want to conclude something to you all guys. So yeah, here you can see that there are two voltages. So remember one thing, that if there are two voltages, then we will require three conditions to analyze this particular circuit. Okay, now let's suppose if there are three voltages, so we will require four conditions to analyze this particular circuit. Okay, as you can see, we have two voltages, therefore we will require three conditions to analyze, just a second, yeah, to analyze the behavior of the circuit, the behavior of the circuit. Okay, so this is a kind of a short note from my side, or you can write it as a short trick or tip. So this can be a trick or a tip. Okay, you can assume it as a trick or a tip, it's up to you, that whenever you see such kind of circuit, and let's suppose as of now we have two voltages. Okay, then we will require three conditions to analyze the behavior of the circuit. If there are n voltages, let me just write over here, yeah, if there are n voltages, okay, then we require n plus 1 conditions to analyze the circuit. Okay, so this is a trick from my side to solve such kind of circuit. Okay, so now we'll see that what all conditions we need to analyze this particular circuit. So for that, we'll go to this particular input waveform. As you can see, this is an input waveform, input voltage plus minus sine omega t. Okay, so as you can see very clearly that this particular waveform is getting divided into two parts. Extremely sorry, it is getting divided into three parts. As you can see over here, the very first part is, see, the input voltage, it is greater than 3.7 volts. So I would like to write over here this particular area where the input voltage, it is greater than 3.7 volts. I'm talking about this particular area. Let me just draw it with yellow color as well, the dotted lines, so that you can easily see this particular thing. Okay, and let me just shade this particular area, this one. Okay, when V in is greater than 3.7 volts, then the very next thing what you can see over here is this. See this one, this one, this one. Right, I will just shade this particular area, this one, this particular area. As you can see, this one. Anyhow, we are not going to deal with area, but yes, for your better understanding, I had drawn this particular thing. Okay, and this is, just a second, so over here your V in, over here your V in, as you can see, it is greater than minus 2.7 volts. It is greater than minus 2.7 volts, correct, but it is less than plus 3.7 volts. So it is less than plus 3.7 volts. I hope you are getting me. See, we are doing nothing. We had just drawn the input waveform, and based on that we are just considering the conditions which I had told to you. As you can see, we had just marked the two voltages, I mean the 2 points in this particular graph, that is plus 3.7 volts and minus 2.7 volts, and based on that we are going to analyze the circuit. But for that, like to analyze this particular circuit, we have to analyze first we have to analyze the input waveform. Okay, so here there are three conditions. So as you can see, we had divided this particular input waveform into three ways. The very first is when V in is greater than 3.7 volts. So that means this particular area or this particular what I can say waveform, okay, forming a cusp, okay. Then this particular waveform which I had shaded in green color. So here your V in is less than minus 2.7 volts, but sorry, extremely sorry, your V in is greater than minus 2.7 volts, but at the same time my V in is less than plus 3.7 volts. That means I'm talking about this particular waveform, okay. And the last is this one. See this particular waveform, that means this one. Let me just shade it with white color only. See this particular graph I'm talking, and here it is V in is less than minus 2.7 volts. And talking about this is nothing but the same, that it will lie in this particular domain only when V in, see this, when V in, oh sorry, yeah, when V in is less than, sorry, when V in is greater than minus 2.7 volts and it is less than plus 3.7 volts. So it is one and the same. I'm not writing it again, okay. So these are the three necessary conditions which we require to analyze this particular circuit. I hope you understood up till here. I hope you understand everything up till here, okay. So now what we are going to do, we will analyze each and every condition one by one, okay. So let's move further. All right, so we'll consider this particular waveform that like when V in is greater than 3.7 volts, okay. So let's suppose your V in is 4 volts. I will write over here, this is when V in greater than 3.7 volts, okay. Let's suppose we'll assume our V in is 4 volts. This is what we are assuming as of now, and let's suppose this is 4 volts, okay. It will come, and let's suppose here we will get plus 4 volts, okay. So now as you can see, here we are providing 3.7 volts and here we are providing 4 volts. Obviously this particular diode, it will get what, it will get switch on, okay. That means it will act as a closed switch. And talking about here, let's suppose here also this particular 4 volts will come, okay, and this 4 volts is connected to the N type of the diode, and here we are providing minus 2.7 volts. This is minus, here we are providing minus 2.7 volts, okay. So this particular diode will remain off, that means it will act as an open circuit. So let me write over here, this particular diode will remain off, closed switch, CS means closed switch, and this particular diode will remain on, that means opens, oh sorry, extremely sorry, this is your open switch, this would act as an open switch and this would act as a closed switch, okay. Let me erase everything because I will consider the same diagram to analyze each and everything, okay. So let me erase each and everything. So yeah, this is what we saw for V in greater than 3.7 volts. So this particular part, it would be closed, I mean this particular diode will act as a closed switch. This particular diode will act as a closed switch. Let me just draw this particular diagram. Yeah, it will act as a closed switch and this will act as an open switch. So due to this, if you could see very clearly what is going to happen, a current is going to flow in this particular direction. See, from here to here to here, okay. So this is your current and this is how your current is going to flow. So let me erase this particular thing and we'll draw only this particular part below. So see over here, it would be something like this. I won't draw this particular diode. Just a second. Yeah, so this is your plus minus 3.7 volts, okay. This was your diode, I'm neglecting this particular diode, and this is your output, V out, okay. And you are checking V out with respect to ground, obviously. and here also it is grounded. Here also it is grounded. Okay, so yeah, as you can see, this is plus minus 3.7 volts. So obviously you can easily see that your V out is nothing but V out is equals to 3.7 volts. V out, I will write over here only, V out is equals to 3.7 volts. You can do this by applying KVL as well, that is minus V out minus 3.7 volts is equals to 0. So you end up getting V out as 3.7 volts. But the most important thing is we have to write these two particular things, that is when our V in it is greater than 3.7 volts. Okay, at that time we get the output as, or V out is equals to plus 3.7 volts. Okay, so we will complete this with the help of one box. This is very important thing, or this is very important point. Okay, what does that mean is, what does that mean is whenever our V in is exceeding, or whenever our V in is greater than 3.7 volts, our output would be 3.7 volts. It would remain constant irrespective of whatever voltage we might give to the input side. If it is greater than 3.7 volts, then obviously at the output side we will only get the constant voltage, that is 3.7 volts. We'll draw the output waveform afterwards, like after some time. We'll first analyze each and every condition. Okay, now let's suppose we are providing the input voltage which is in between minus 2.7 volts to plus 3.7 volts. Okay, that means we are analyzing this particular waveform. See, we are analyzing this particular waveform, this one. Okay, so this is what we are going to do. So let's suppose for this I will consider over here our V in, it is greater than minus 2.7 volts. 2.7 volts is less than V in, and V in is less than plus 3.7 volts. Okay, so now let's suppose if my V in is let's suppose it is 0 volts, because anyhow 0 lies in between plus and minus. Okay, let's suppose if I'm giving 0 volts, that means I'm talking about this particular point. See this one, this particular point. Okay, so let's suppose if I'm giving 0 volts over here, let's suppose here it is 0 volts, and here also, since it is kind of short circuit, so here also you end up getting 0 volts. Okay, so now if you could see very clearly that to the N side of the D1 you are giving positive voltage, and to the P side you are giving almost negative voltage, although it is 0 voltage, but you consider it as a negative for instance. Okay, so due to this, what is going to happen, this particular diode will remain off. This particular diode will remain off, or what I can say, it will act as an open switch. OS means open switch. Okay, why? Because you are giving lower voltage to the P side and higher voltage to the N side. Similarly over here, as you all know that 0 is greater than minus, it is minus 2.7 volts. Okay, so due to this, what is going to happen, again this particular diode is going to be off, because we are providing higher voltage to the N side, okay, and lower voltage to the P side. So again this diode will remain off, and due to this it will act as an open switch or open circuit. So yeah, this circuit will remain as it is. I will just draw 2 points indicating that this particular diode will act as an open switch, something like this. And now if you could see very clearly that whatever the current that is coming from V in, just a second, whatever the current that is coming from V in, it will follow this particular path. Just a second, it will follow this particular path. Okay, let me just draw neatly over here. So this, let's suppose this is your input. Okay, and there is diode D1, but it, for instance, like since our V in is 0 volts, due to this particular thing, it is acting as an open switch. Okay, and again over here the diode D2 is off, so again it is acting as an open switch, and this is our V out. This is our plus minus V out, and again this particular whole of the thing is grounded. Okay, and this is nothing but our V in, plus minus V in. So obviously whatever the current that would be flowing, it would flow in this particular direction. It will never ever flow in these two particular parts. It will never ever flow in these two particular parts. Okay, because they are acting as an open switch, or it is like an open circuit for the current. Therefore it will provide high resistance. Okay, I hope you are getting me. So what we saw is this: when the for this particular condition, that is minus 2.7 volts, if it is less than V in, and V in is less than plus 3.7 volts. So for this particular condition, what we saw is this: whatever the input voltage we are giving, it is straight away getting reflected to the output side, V in. Okay, here also it's up to you, can apply KVL. See over here, minus V out. Let's suppose you are applying KVL in this particular direction, so minus V out minus V in is equals to 0. Therefore your V out is equals to V in. Oh sorry, it is plus, extremely sorry, it is plus, since we are applying KVL in this particular direction. Extremely sorry, so it would be plus V out, then we are going in this way, and it would be minus V in. So plus V out minus V in, we are getting V out is equals to V in, or straight away you can directly apply the logic of parallel. See, these both are in parallel connection, or they are connected parallelly. So again, whatever the input voltage we are giving, it is straight away getting reflected to the output side. Okay, so I hope you understood each and everything up till here, and now we are only left with the last condition, which we are just going to analyze now. Just a second, let me just complete this particular box. Yes, okay, and this is another important condition, and now we'll jump to that particular graph. Yeah, so this is this particular graph, and now what we'll do, we are analyzing this particular part. If you could see very clearly, just a second. Yeah, we are analyzing this particular part of the graph, this one. Okay, that means when we in, oh sorry, extremely sorry, see this particular graph. I hope now, I think now it won't get erased. Anyhow, I hope that you understood it. We are analyzing this particular part. So yeah, this is what we are analyzing, that when V in, it is less than minus 2.7 volts. Okay, so let's suppose we are giving input voltage as minus 4 volts. So let's suppose here we are giving, now I will erase this particular thing, erase this as well. Just a second, I will erase this quickly, and then we will solve for this particular condition. Okay, fine. So let's suppose to the input side we are giving minus 4 volts, since our V in is less than minus 2.7 volts. So let's suppose to the input side we are providing minus 4 volts to the input side, so it will get reflected over here. Of course there might be some drop. Okay, there might be some drop due to this resistor, but that can be neglected as of now for analyzing this particular circuit. Okay, so again, as you can see, we are providing higher voltage to the N side of the diode D1, and we are providing very low voltage to the P side of the diode D1. So due to this particular diode D1 will remain off again, and it will act as an open switch. And talking about diode D2, we are providing higher voltage to the P side of the diode, minus 2.7 volts. Minus 2.7 volts is obviously greater than minus 4 volts. So that means we are providing higher voltage to the P side. So this is our P side, this is our N side of the diode, and therefore this diode D2 will remain on. That means it will act as a closed switch. okay, and thus it will allow the current to flow. So let's go to this particular diagram, and as I told to you, this diode D1 will remain off, so it will act as an open circuit, and this diode D2, it will switch off. I mean to say, sorry, it will this will act as a closed switch. Okay, so now if you could see very clearly, the current will flow in this particular, oh sorry, the current will flow in this particular direction. Okay, I hope you are getting me. I mean, it will flow in this particular direction. So our V out would be, just a second, what I will do, I will draw this particular circuit over here so that there won't be any confusion. See, I'm not drawing this particular diode, but this is your minus 2.7 volts, and this is your V out, and these two things, they are grounded. So this is your plus minus V out. Again, by applying the parallel logic, I mean the parallel combination, since they both are connected in parallel. Okay, so you can directly get V out as minus 2.7 volts, or if you want, you can apply KVL. That means plus V out. Okay, plus V out, then plus 2.7 volts, which is equals to 0. So at the end we get V out. At the end we get V out as minus 2.7 volts. So this is what we are getting. Okay, when our V in is less than minus 2.7 volts. So let me write over here, when V in it is less than minus 2.7 volts. So in this case we are getting V out as V out is equals to, oh sorry, yeah, V out is equals to minus 2.7 volts. Okay, so let me highlight it with a box, and I think now we are good to go, and we can easily draw the output waveform for this particular for that particular input waveform. Okay, yes, so let's straight away go to that particular graph, and then we are good to analyze this particular graph. See, the very first thing you can see that from this particular waveform is moving from 0 to plus 3.7 volts. That means it is operating in this particular condition. Since 0 volt is lying between minus 5 to plus 3.7 volts, so therefore, as you can see, during this particular period or during this particular time interval, your V out would be equals to V in. Okay, so that's why whatever the input waveform, that would be getting reflected as it is to the output side. So we'll draw a straight line. Okay, something like this. And after that, when V in is greater than, or if V in is exceeding plus 3.7 volts, that means this particular condition, this one, when V in is greater than plus 3.7 volts, so at the output side you are getting plus 3.7 volts. So we'll draw a line something like this, indicating that this is plus 3.7 volts. And now again, see here, the V in is in between plus 3.7 volt and minus 2.7 volts. That means this particular condition, that our V in is lying in between minus 2.7 volts to plus 3.7 volts. Okay, so for this, if you see very clearly, our V out is equals to V in, so that's why we'll draw the waveform as it is. So something like this, yeah, something like this. And then if you could see very clearly, we are dealing with this particular part. That means when V in is less than minus 2.7 volts. So this particular condition, yeah, when V in is less than minus 2.7 volts. So for that particular condition, we are getting V out as minus 2.7 volts. So we'll draw this particular complete this particular graph. So we end up getting this particular minus 2.7 volts. Okay, something like this. And then again it is less than that, so we'll draw this particular line something like this. Just a second. Yeah, something like this. Okay, student. So I hope that you understood each and everything up till here. And now what we are going to do, obviously we are going to draw the transfer characteristic for this particular circuit of the, or for this particular clipper circuit. Okay, so let's straight away come to the transfer characteristic. And yeah, as you all know that this is very tough part for me to draw the input waveform, but still I will try my best. Oh, sorry. So something like this is my, oh, will decrease the width of the waveform. Yeah, something like this, and then I will draw the projection line. This one and this one. Okay, so these two particular points which you are seeing over here, they are indicating that, just a second, yeah, these two particular points, they are indicating that to the input side we are giving the waveform of plus 5 volts. So this is plus 5 volts and this is minus 5 volts. See, it is nothing but, just a second, I will go directly to that particular page. Yeah, see, this particular waveform you are drawing in this way. Now you just have to tilt it, or you just have to rotate it by 90 degree. Okay, something like this. I hope you understood up till here. Okay, so this is what we had done as of now, and then we'll again go back to that particular transfer characteristic page. Yes, and now what we have to do, we have to draw the output waveform. So we'll check what kind of output waveform we are getting. Okay, so it is something like this, plus 3.7 volts, then minus 2.7 volts. Okay, so we will try to draw a similar kind of waveform, although it won't be that much accurate because I would be drawing it roughly, but still it will help us to understand the transfer characteristic. So this is something like plus 3.7 volts. It will remain as it is for certain time, and then it would be minus 2.7 volts. Oh, sorry, minus 2 point something like this. Yes, minus 2.7 volts, and then this will go on continuing. Okay, so this is what we want. So again we'll draw the projection line. So this is plus and this is, oh sorry, minus 2.7 volts. Okay, so this is plus 3.7 volts and this is minus 3.7 volts. And let me just draw everything, and let me just mark those points. So this is plus 3.7 volt plus 3.7 volts, and this is your minus 2.7 volts, something like this over here, minus 2.7 volts. Okay, and here also to the input side, what you have to do, you have to draw two lines, so indicating that this is your plus and minus 3.7 volts. So something like this, plus 3.7 volts, it may lie somewhere over here. Okay, and minus 2.7 volts, that means it may lie somewhere over here. I hope you are getting me. So let me just mark those particular points. This is your minus, just a second, this is your minus 2.7 volts and this is your plus 3.7 volts. Okay, and now if you try to draw the projection, I mean if you try to draw according to the projection, so this would be something like this. See, at the input side you are giving plus 5 volts, so it would be getting reflected as it is, and to the output side it is minus 2.7 volts. And as soon as the input waveform, it is increasing from minus 2 to plus 3.7 volts, so it is following the input and output waveform, extremely sorry, the output waveform, it is following to the input waveform, so it would remain as it is in between this range. That means from minus 2.7 to plus 3.7, and as the input waveform, it is going from plus 3.7 to plus 5 volts, it is getting clipped. Okay, it is getting clipped, as you can see, and this is how it will look in the transfer characteristic. Let me just show the projections with the help of dotted lines, otherwise this would be kind of chaos in between. Okay, so that there won't be any kind of chaos or confusion with the because many lines are intersecting each other. So let me just erase this particular thing, or let me just show with the help of dotted lines. Yes, something like this, and I will explain this transfer characteristic again, but let me mark those particular points. But I will just erase these two particular points because it is not required as of now over here. Yes, I will mark those points over here. Let me mark with the green color this point and this point. Okay, and this is plus 3.7 volts, and this is your minus 2.7 volts. Okay, so these are the 2 points. See, we'll just go to that particular graph which we had deduced. See over here, when your input voltage is in between plus 3 volts to minus 2.7 volts, 3.7 volts to minus 2.7 volts, so your output wave, it is following the input. See over here as well, when your your input voltage, when it is in between plus 3.7 volts to minus 2.7 volts, so your output voltage, it is following the input voltage. So that's why we draw this particular waveform as it is. But when V in is greater than 3.7 volts, so your output voltage, you are at the output side, you are getting plus 3.7 volts. And over here as well, when your V in is less than minus 2.7 volts, so at the output side you are getting minus 2.7 volts. Just remember this, and then we will see over here. See over here, when our input voltage, when it is less than plus 3.7 volts, so this is, as you can see, plus 3.7 volts, so our input wave, it is following the output wave, or our input voltage, it is following the output voltage. See over here, it is following as it is. But as soon as our input voltage is greater than plus 3.7 volts, that means this particular area or this particular waveform, the waveform is getting clipped at the output side. See over here, it is getting clipped at the output side. Let's suppose if the output waveform, it is not clipping, and let's suppose it is getting reflected as it is to the input side, sorry, as it is as compared to input. So this particular transfer characteristic, it would be something like this. See, it might have joined something over here, and then this particular projection would be, just a second, yeah, something like this. Okay, I hope you are getting me. Okay, the transfer characteristic would be something like this. Okay, but since it is been clipped, just a second, let me erase this. Yeah, since it is clipped, so that's why it is we are getting transfer characteristic as it is, or we are getting this particular, what you can say, a line indicating that the slope is 0. Okay, otherwise if this waveform would be something like this, then we might have got the projection somewhere over here, and again the slope would be same as we are getting over here. Okay, so now dealing with this particular part, this particular waveform from plus 3.7 volts to minus 2.7 volts, this particular waveform, it is following as it is. That means your input output waveform, it would be same. See this particular point, this one and this one, or your output waveform will follow the input one. And as soon as your input waveform, if it is getting less than minus 2.7 volts, so as you can see over here at the output side you are getting minus 2.7 volts. Okay, that means your negative part of the waveform, it is getting clipped. Let's suppose if it is not getting clipped, and let's suppose if it would be something like this. Okay, that means your negative side is not clipped and it is getting reflected as it is. So what you can do, you can draw this line over here, and then you can extend this particular line over here, indicating that the slope is constant. Okay, but since what, since your negative side is getting clipped, so that's why your slope automatically becomes 0, and this is how it is indicated in the transfer characteristic. And I had already told you what is transfer characteristic in the previous session. So now I really hope that you understood each and everything about this particular circuit, how how to proceed whenever you get such kind of circuit. Okay, so I really hope that you enjoyed this particular session. If you have any doubts, feel free to ask me at any time. I'm here to help you throughout this particular session. Okay, so thank you for listening to me patiently. I'm ending this video over here. Thank you.